The Webb glance is such a long way out that it's catching light that has been voyaging for over 13 billion years. Yet the universe has been expanding, and thus the light has been stretching. For the most distant worlds, we're looking back in time nearly to the Big Bang. The immensity of the universe might seem vast, but every last bit of it started from what we allude to as the singularity. As of now, this is how we interpret the Big Bang hypothesis. Anyway, the James Webb Space Telescope, JWST, has revealed significant mysteries about the birth and development of the universe, leaving us dumbfounded. Prestigious physicist Brian Cox has proclaimed that the noteworthy discoveries made by the JWST might actually reshape our understanding of the universe as a whole. Join us as we dive into these new heavenly discoveries that promise to change our comprehension. The James Webb Space Telescope, named after the recognized NASA executive James E. Webb, stands as a wonder in current galactic investigation. This telescope represents a huge mechanical leap forward from its ancestor, the Hubble Space Telescope. Resulting from a cooperative effort between NASA, the European Space Agency, and the Canadian Space Agency, the JWST surpasses the abilities of its herald. It utilizes cutting-edge technology and a design enhanced for observing the universe in remarkable detail. Unlike the Hubble, the JWST conveys clear and sharp images of far-off celestial bodies. Working primarily in the infrared range, this component allows it to penetrate astronomical dust and capture divine objects previously hidden from our view. With its massive 6.5-meter primary mirror made out of 18 hexagonal sections, the JWST far exceeds the Hubble's reflector size. Situated roughly 1.5 million kilometers away from Earth at the second Lagrange point, L2, it orbits the Sun in synchrony with Earth, ensuring a stable and continuous view of the universe. While looking into the far-off corners of the universe involves exploring light years, it also involves a type of time travel. The JWST uses infrared instruments to observe celestial objects and events going back billions of years. The light emitted by these objects, because of the expanding universe, undergoes redshift, moving from the visible range to the infrared. Luckily, the JWST can detect infrared light radiated by celestial bodies at extreme distances, empowering researchers to study the formation of stars, investigate galaxy development, and examine exoplanet atmospheres. Its latest historic discovery involves identifying an incomprehensible mass of cosmic systems at the edge of the observable universe. This finding challenges the validity of the current theory of how things came to be, provoking a reassessment of our key cosmological assumptions. To better understand how we arrived at this point, we should take a short excursion through the history of space investigation. Early civilizations like the Greeks and Chinese laid the foundation for understanding planetary movement by observing celestial bodies. Newton's laws in the 17th century gave a theoretical structure for space travel. In the mid-20th century, Edwin Hubble, an influential astronomer, made historic revelations in cosmology and observational space science. His observations uncovered that far-off nebulae were actually isolated galaxies beyond the Milky Way, changing our understanding of the universe's size and expansion. Hubble's law, established by him, showed that galaxies farther away were moving faster, giving proof of the universe's expansion. The post-World War II history of space exploration marked the beginning of the space race. The Soviet Union launched Sputnik in 1957, the first artificial satellite in orbit. Yuri Gagarin's orbital trip in 1961 and the Apollo 11 moon landing in 1969 were crucial accomplishments. Fast forward to 1990, the Hubble Space Telescope was launched, offering exceptional clarity and insights into the universe. The journey from ancient observations to the technological marvel of the James Webb Space Telescope showcases the continuous development of our cosmic understanding. The Hubble Space Telescope, for instance, captured the famous Pillars of Creation image in the Eagle Nebula, revealing a star nursery formed by massive columns of gas and dust. Another significant accomplishment was the Hubble Deep Field, capturing a huge number of galaxies in a seemingly void patch of space. The HST also studied exoplanet atmospheres, detecting elements like water and organic molecules in distant worlds, alluding to the possibility of habitable zones beyond our solar system. By following the development of the closest observed supernova, SN 1987A, it shed light on the life cycle of massive stars. These achievements cemented the Hubble's legacy in modern cosmology, dazzling the world with enormous discoveries. Its successor, the James Webb Space Telescope, was launched to build upon those technological advancements and lessons. According to the prevailing theory, around 13.8 billion years ago, the universe began as a hot, dense singularity, rapidly expanding and giving rise to matter, energy, and the fundamental forces. As the universe expanded, it cooled, leading to the formation of atoms, stars, galaxies, and cosmic structures we observe today. The Big Bang Theory explains cosmic microwave background radiation, light element abundance, and the large-scale structure of the universe. Though widely accepted, the Big Bang Theory faced skepticism early on. Alternatives like the steady-state theory proposed a universe without a specific beginning. Most objections were addressed over time. A major breakthrough came with the detection of cosmic microwave background radiation in 1965, matching Big Bang predictions. Space missions like COBE and WMAP further supported the theory. Enter the JWST. Equipped with advanced infrared instruments, it captures the oldest light in the universe and observes objects formed shortly after the Big Bang. Its infrared abilities let it focus on star-forming regions hidden from optical telescopes. Infrared light, with its longer wavelengths, can penetrate interstellar dust, something the Hubble struggled with. The JWST can observe cooler objects like exoplanets, brown dwarfs, and distant galaxies. As celestial bodies move away, their emitted light stretches, causing a redshift. The JWST detects these redshifted signals, capturing light from the early universe and offering new insights into its evolution. Energetic events like black hole mergers or new star births emit primarily in the infrared, making the JWST ideal for their study. The telescope supplements optical telescopes like the Hubble by adding enhanced sensitivity to infrared radiation. This allows it to peer further into space and deeper into astronomical history, providing a comprehensive view of the universe's development. Recently, the JWST made a discovery so profound it might prompt a reconsideration of the entire cosmological model. We've discovered massive clusters of galaxies at the very edge of the observable universe. These ancient galaxies formed just a few 100 million years after the Big Bang during the cosmic dawn. The puzzling part is how such enormous structures could form so early. Studying early galaxies is essential for unraveling the mysteries of cosmic origins. The JWST helps uncover how galaxies, stars, and planetary systems formed and evolved over billions of years. These observations also contribute to broader questions about the nature, composition, and structure of the universe. While the Hubble was groundbreaking, it had limitations in penetrating cosmic dust and detecting infrared light. Older telescopes relied on visible and ultraviolet light, which struggles to pass through interstellar dust. The JWST represents a leap forward, observing galaxies from the universe's earliest stages. Using its advanced imaging capabilities, the JWST has uncovered an abundance of ancient galaxies with remarkable clarity. Early results have shaken established cosmological models. Some galaxies appear more developed than expected, challenging the assumption of a slow evolution. The discovery of vast ancient structures reveals a denser cosmic web than previously believed. These discrepancies suggest unknown physical processes or unexpected cosmic phenomena. In simple terms, scientists are rethinking and refining our models of the universe. Early observations often reveal exciting glimpses, but deeper investigations can show unexpected complexities. Spectroscopy, a method of analyzing light emitted or absorbed by celestial bodies, helps us understand their composition, temperature, and movement. Using this technique, the JWST has found elemental variations in early galaxies, identifying heavier elements previously undetected. This challenges assumptions about the early universe's chemistry. Initial assumptions about uniform galaxy development were appended by JWST's findings of diverse chemical compositions across early galaxies. The telescope continues to redefine our cosmic understanding by revealing previously hidden phenomena. One of its most exciting capabilities is analyzing exoplanet atmospheres. It can detect key chemical signatures like water vapor, carbon dioxide, methane, and other organic compounds, clues to potential habitability. Additionally, the JWST is revolutionizing our knowledge of star formation. It observes young stars forming in dense clouds of gas and dust invisible to optical telescopes. By capturing their earliest stages, astronomers gain insight into stellar and planetary system evolution.